So covalent bonds, we talked about this already a couple slides ago, or a couple questions ago, but covalent bonds happen when there's only nonmetals. There's no metal, nonmetal or metals are not present because normally they would give the nonmetals the electrons they need. When the nonmetals need 1, 2, or 3 electrons to become stable, they usually get them from metals, but if there's no metals, then they've got to cooperate. They're going to pool the electrons together, they're going to share them, and all the elements are going to end up with an octet. Now, they're going to be shared evenly if both atoms exert the same attractive force on the shared electrons. So if this little penguin and that little penguin are equally matched, then they share the electrons together and they share them evenly. That means their EN values, which we'll see in a minute, their EN values, electronegativity values, are roughly the same. Electrons will spend half their time here, half their time there. They go back and forth. That's like these two chlorines. This chlorine's got 7 valence, and this chlorine's got 7 valence electrons. And they both wish there was a metal there to give them an electron and put it right there. But there is no metal, so the two chlorines look at each other and say, I know, let's share. You send this electron around me, and it'll make my octet, and I'll send mine and yours back, and it'll go around you, and you'll have the octet. And both of us think we have 8, because these two get shared back and forth. And we end up showing that as a covalent bond. So those electrons spend half their time around one atom and half their time around the other, and we usually depict that with a line representing those two shared electrons. Now, if they're evenly matched, and a chlorine and a chlorine are evenly matched, they're shared evenly. But if they're unevenly matched, let's say this is a chlorine and an oxygen, then the electrons end up, actually this is the oxygen, this would be the chlorine, because oxygen's a little stronger. But the electrons would end up spending more of their time around one of these atoms than the other. They still go back and forth, they're still shared, but they spend more of their time around the stronger one, less time around the weaker one. How do we know who's strong and who's weak? Well, we think about electronegativity. Electronegativity is how strongly an atom can attract additional electrons. So if I'm chlorine, can I pull on these electrons here? If I'm little hydrogen, can I pull on those electrons here? Now, both can exert a force, but chlorine can exert a stronger force. And we'll talk about why in a second. But these ice cream cones, or ice cream scoops, are really electrons, and they're being pulled towards a particular element and away from another one. So that's what electronegativity is, trying to pull more electrons in, trying to pull that ice cream cone in. So what happens as we go across? Well, the nucleus gets stronger. And as the nucleus gets stronger, it does a better job pulling on an additional electron. So if here's an electron and that nucleus wants to pull this guy in, it can do it because there's 9 protons in fluorine. Lithium only has 3. So if lithium's trying to get another electron, it can't pull it in as well. Not as well as 9, not as well as fluorine, because this has a stronger pull. So as we go to the right, we see the polar bears. Penguins are over here. These guys are weak. Polar bears are stronger. So as we go to the right, there's more protons, so they make a stronger pull. Now, as we go down a group, we basically have the problem of electrons in the way. So here's the nucleus trying to pull on an electron here. Now, the nucleus has 2 energy levels in between it, and then it can exert a force. This nucleus, if it wants to pull on another electron, it's got all these energy levels in the way. So this nucleus can't do a really good job pulling more electrons in. So these guys are very weak, and up at the top, these guys are very strong, comparatively speaking. So if we're on this side of the table, periodic table here, we're comparing penguins. We're comparing lithium and all of these, hydrogen to start with, and then lithium and so forth, and all the way down. And here's the weakest little penguin. He's on this side. He doesn't have a lot of protons. His nucleus isn't really strong. And he's at the bottom, which means he's got tons of electrons in the way. So he does a horrendous job trying to pull on ice cream or trying to pull electrons in towards him. He always loses his ice cream. Always. Now over here, let's talk about the big guy. This is the biggest polar bear. This is fluorine. He gets a 4.0. He's on this side, so his nucleus is really strong, and he's up top. He doesn't have a lot of electrons in the way. This is fluorine, so he's got an electron configuration of 1s2, 2s2, 2p5. he's only got 2 energy levels of electrons, whereas people down here might have 5 or 6 or 7 energy levels. Tons of electrons in the way. So they can't do a really good job pulling on another one because there's so much of that shielding effect going on. So if we want to have a tug of war, we want to be fluorine. We want to be able to pull the electrons in, pull the ice cream towards us, and get those extra electrons in the electron cloud and make that 2p5 turn into a 2p6. Or at the very least, share electrons and think that you have your full octet all the time. So when you're thinking about the trends for electronegativity, think about pulling on ice cream cones or the scoops of the ice cream, which are the electrons, and who's going to be stronger. And it's always up at the top and over on the right. It's always fluorine because he's got the most protons and he's got the fewest electrons in the way. And the little weak guy, poor little guy down here, never wins. And we're going to talk about this a lot more when we get into Unit 5, Section 2 and 3 a little bit. Okay? All right, that's it. Good luck.